Hello, everybody. Welcome to today One Word Mathematical Physics seminar of the International Association of Mathematical Physics. Our today's speaker is Joseph Tooby-Smith from the University of Bath, who will speak about digitalizing physics into Lean 4. Please go ahead, Joseph.
Great. Yeah, first of all, thank you for inviting me. And yeah, I'm going to speak about digitalizing physics into Lean 4. If you don't understand what that means, don't worry. I'm going to kind of explain what this whole area of formalization or digitalization is in this talk. If you have questions, feel free to interrupt me. I have a tendency to speak kind of quickly when I get excited about a topic. So if you miss something, also feel free just to stop me. I'm going to split this talk into three thirds. The first third, I'm going to explain what an interactive theorem prover is. This is the programming language or the type of programming language where people write or formalize things from mathematics and physics. I'll explain what all of that is in the first third. In the second third, I'll explain this project Physlib. And then in the third third, I will look at some results that we have in Physlib, kind of just do an overview of some of the things that we've actually got within the project. Before I get into the nitty-gritty detail, I want to start with a story. And this is a story that I often tell when I give talks. It is about an archive paper, HEP PH 051221. Don't worry about the HEP PH. This is not particle phenomenology. This is a lead-in to something else. The paper is a QCD summary study of light scalar mesons. You don't need to know the details. All that you need to know is that in this paper, Hee-Jung Lee calculated this quantity E by adding together some terms A1, A2 through to AN. The story that I'm interested in is a story about what happened after this paper was put onto the archive. Because shortly after this paper appeared on the archive, another paper appeared. A comment on the QCD summary study of light scalar mesons. What that comment said was that original paper was incorrect, that there was a mistake in it, that Hee-Jung had missed two terms, B1 and B2, which when added to the quantity E, invalidated the conclusion of the original paper. Shortly after this comment appeared on the archive, another paper appeared on the archive. A reply to the comments on the QCD summary study of light scalar mesons by the original author of the first paper, saying those two terms shouldn't be there. The original paper was correct and the comment was incorrect. At this point, you can probably guess where this is going, because shortly after this reply to the comment appeared on the archive, another paper appeared. A reply to the comment on a QCD summary study of light scalar mesons, saying those terms should be there. The original paper was wrong, the comment was right. In the end, the authors of the comment and the fourth paper and the fourth reply to the comment realized that they had made a mistake, an error in their paper, that those two terms, B1 and B2, shouldn't be there, and the original paper was correct. So why am I telling you this story? The reason I'm telling you this story is that within physics and within academia, papers or errors in papers happen all of the time, whether they're simple typos or whether they're more conceptual mistakes. Errors in papers are things that happen because we are human and they're always going to happen. So the key concept I want to bring in here is the concept of trust. And with this level or with this statement that papers generically have errors in them, our level of trust of papers should be very low. But in academia, for centuries, we've had some mechanisms in place to increase the level of trust that we have in academic papers. The first one is trust by authority. This is basically the peer review process. You see a paper is in a given journal, you trust that that journal has looked at that paper, it has been sent out to some reviewers, and you are trusting the authority of the journal to say that that paper is correct, the content of that paper is good. That's the first way we put trust back in papers in academia. The second way is trust by reputation. And this is for something more akin to the archive or a preprint server, where you're looking at the authors of the paper, you're going, yes, they have published papers in the past of a good quality, so their reputation can be used to help trust this paper. The third area of trust, the third way we put trust back into papers in academia is by replication. Being able to trust the paper by looking at the calculation, looking at the proofs, looking at the derivations oneself, or if it's experiment, doing the experiment oneself, and checking that those proofs make sense and that they hold. So these are kind of the three ways, or the three main ways that I could think of that we put trust back into papers in academia. That was all well and good until up to about 2022, when AI became a much bigger thing. With the AI revolution, two things happened. Firstly, the volume of papers dramatically increased. So recently, we've had the largest number of papers ever posted to the archive, reaching up to 30,000 per month. A lot of this is contributed to because of artificial intelligence. More and more people are using AI. And the problem with that is that AI hallucinates. Less now than it used to, but it still hallucinates. And that means it says stuff that can be wrong. These errors that happen in papers, you hear about these citations being incorrect in papers, that's about citations. What about the mathematics? What about the underlying physics? So what I want to say kind of in this talk is that with this AI revolution, we also need a revolution in trust. We also need to come up with a way that we can retrust the papers, retrust the results that we have in academia and in physics. And really, this poses this question. I'm going to just move the Zoom thing a second. What can we do to increase this trust back up? With this increase of papers, that our previous methods no longer scale to. We can't expect with this increase of AI, these previous methods of trust to scale. What can we do to increase trust? I'm going to give you a single answer, but this is by no means the complete answer or the complete story to this question, and that is to use something called interactive theorem provers. This doesn't increase trust all the way up to infinity, all the way up to complete trust, but it does allow us to have some level of trust in the outputs of either humans or of artificial intelligence. And it's scalable. And I'll explain why it's scalable in a second, but it's a scalable way to increase trust in academic papers or academic results more generally. So what is an interactive theorem prover? This thing that I've been talking about. First and foremost, an interactive theorem prover is a programming language. So it's akin to something like Python or C++ or something like that. The key thing about an interactive theorem prover is that into it, you write mathematical definitions, theorems, and proofs. And the interactive theorem prover would check those for mathematical correctness and mathematical consistency. And we'll see this explicitly in a second. You cannot write something that is mathematically inconsistent into one of these interactive theorem provers, and you cannot prove something that is incorrect in one of these interactive theorem provers. This gives you a way, an automated way to check the mathematical content of results in mathematics and in physics. There are a number of interactive theorem provers out there. The one that you may have heard of historically is Isabelle. The one that you may have heard of being put around more recently is this one called Lean, but there are others, and they all differ slightly in how they work and the underlying mathematical content of their definitions. So this Rock, for example, and Agda are also examples of interactive theorem provers. For this talk, I'm going to focus on Lean because that's the one that I think is increasing in popularity, and it's also the one that I happen to work in. Lean has recently had this increase in popularity. You may have heard on the news that things have been solved using formalization. If that's the case, it usually happens that it's been in Lean. Not always, but a lot of the time it's in this programming language called Lean. And I like to think of Lean's rise in popularity as down to two factors. The first one is Mathlib. I'll explain what Mathlib is in a second. The second is AI. That's kind of the obvious one that I kind of led this talk on. But I want to first explain Mathlib. What is Mathlib? So the way I like to see Mathlib is what happens when you take the open source community and the open source workflow from computer science and you bring that into mathematics and you say, what can we do with that sort of workflow, that sort of way of thinking? And what you can do is that you can create a library of results from mathematics formalized into Lean. So it's results of mathematics written in this interactive theorem proof of Lean that we know is mathematically consistent, we know is mathematically correct, and we can reuse to do other things. The project was started in 2017, and these statistics are slightly out of date, but it's had over 500 contributors, has got over 100,000 definitions from mathematics and over 200,000 theorems from mathematics. And it covers a range of different areas from algebra to algebraic topology, category theory, field theory, information theory, measure theory, so on and so forth. It covers some areas more than others. For example, it's got more number theory than it's got differential geometry, but it's still got a large coverage of a lot of different areas. So much so that you can start to do high-level mathematics using this library. So that's factor number one, leading to Lean's rise in popularity. Factor number two is AI. And the reason for this is simple. You can have a feedback loop where AI writes code into Lean. Lean, remember, only accepts things which is mathematically correct and mathematically consistent. So if you want to prove a theorem, you can take that, you can write the statement of that theorem in Lean. You can ship that theorem off to an AI. You can ask the AI, produce a proof of this theorem. It will try and produce a proof of that theorem within the syntax of Lean. It will ship that proof back to Lean. Lean will go, yes, this proof is correct, or no, this proof is not correct. And if it's not correct, it will send it back to the AI, back and forth, without any human involvement. And this way, you can start to solve problems in mathematics. You can start to prove stuff in mathematics, and then of course, also in physics. And you may have heard results like the Urjosh problem's been solved. There's been a number of these cases recently. Not all of them have been solved with this feedback loop, but certainly some of them have. And an example of this is Urjosh problem number 728. So this is really the rise in Lean's popularity, and this is why Lean is kind of getting more and more talked about and getting more and more evolved. And of course, you don't have to use Lean here. You could replace that with some other proof system. It just happens to be that because of Mathlib, Lean is the one that people are going to. So it's all well and good me kind of saying this to you, but I wanted to show you something explicit. I wanted to show you some Lean code to kind of show you what these things can actually do. So to do that, I need to come out and I need to refresh. And then I need to make my screen again. So if you're following along on my slides, you can actually open this as well. This is an info. This is something provided by the Lean FRO. It is an online Lean kind of playground where you can play with Lean online. And the file that I'm showing you is something related to the Higgs boson. It proves a theorem related to the Higgs boson potential. But I want to start with much more basic things about kind of what Lean gives you and what it shows you. So the first thing I want you to notice is that there are two halves to this screen. On the left-hand side, there is the Lean file, and on the right-hand side, you've got this thing, this sidebar. That is called the info viewer. Kind of as the name suggests, there's going to be information that's going to come up there. In particular, something called the tactic state is going to come up there. And that's going to help you, or even help the AI, interact with proofs as you go along. Lean is based on these things called type theory. And so if you don't know what type theory is, don't worry. You can think of a type as very similar to a set. So for every set that you might have in physics, for example, the set of real numbers, the set of complex numbers, the set of far fermions, the set of the gauge group of the standard model, in Lean, you've got a type. And what you're looking at on the screen right here, hopefully you can see this, is the set or the type that corresponds to the gauge group of the standard model. So it's saying this is what we're going to call it. We're going to call it gauge group I. The I here, by the way, is because I'm quotienting it by the identity discrete factor. If you know things about the standard model gauge group, it's only defined up to a discrete quotient. This is to say I'm taking the identity quotient. So we're going to define this thing here. It's going to be a type, and it's going to correspond to this thing here. So this here is SU3, this is SU2, and this thing here is U1. In other words, the gauge group of the standard model is SU3 plus SU2 plus U1. And you notice that here, the special unitary group, that's defined in Mathlib, and we're importing Mathlib here so we can use that without having to redefine it. So with that set that corresponds to the gauge group, I can start to define properties on that set. We know, for example, that this gauge group is in fact a group. That's not defined so far, and to do that in Lean, you have to define what's called an instance. And you can define instances for all of the things that you'd expect a set, all the sorts of properties you'd expect a set to have in mathematics. So here we're going to define an instance of a group on this gauge group. And we could do that manually by saying this is the multiplication rule, this is the identity, this is what the inverse is, and so on and so forth. Or in this specific case, we can just say, infer it from the fact that this gauge group is defined as SU3 plus SU2 plus U1. And Lean is smart enough to do that inference for us and to take the property of the group on that and bring it over to gauge group. Awesome. So that's kind of like a type, and that's kind of like an instance. And this sort of type theory thing is basically the foundation of how Lean is working. So if I wanted to write something like if I wanted to say let G be an element of the gauge group G, I would write something like this. This is general type theory notation, and this says G is an element of this gauge group. And I could, for example, write down the proposition. Let's say I could write down that theorem. This theorem says that the SU2 component of this gauge group element is equal to 1. I wouldn't be able to prove this theorem, which is why I've written sorry, because it's not true for every gauge group element. But you can start to construct equations and things like this using these sorts of structures. To give you a more concrete example, given the gauge group, we can define another type. And this is generally true in a language like Lean. Given one type, you can start to construct other types. And here, I've constructed the type which corresponds to homeomorphisms from the gauge group to SU2. And this is basically going to be the thing that I defined earlier. It's going to be that projection down onto that SU2 factor. And here I have to prove some results about this, mainly that 1 maps to 1 and multiplication is preserved. And this notation here is basically saying we're going to define this element, we're going to call it 2SU2. It's going to be an element or a term of this type. And this here is the definition of that type. So with that, we can give our first example of Lean checking for consistency. So if I let G be an element of SU2 and I put it as an argument of this function, you will notice that Lean has put a squiggly line under it. It's put a squiggly line under it in the same way that that Microsoft Word or LaTeX would put a squiggly line if you made a spelling mistake. And this is Lean saying this is not consistent because here it is expecting, you can see, it's expecting something which is part of the gauge group, but you've given it something which is part of SU2. And it doesn't like that. And this is basically how Lean is doing these mathematical checks. It's checking the type of things, and it's checking in every slot, do I have that thing? Do I have the type of the thing that I should have? So something that's more correct would be this, where I've got an element of SU2. I've constructed from that an element of the gauge group, which is this here, and then I've applied 2SU2 here. And this here is actually a proof that this is true, and it's going to follow by definition. Awesome. I understand that things like this can be quite hard to follow, especially because I have to condense this into an hour talk. So if you're not following me, don't worry. Everything else that's going to depend on this talk does not depend on what I'm showing you here. I just want to give you a more hands-on example of what I'm showing. So the other thing I want to show you then is a theorem. And that theorem, so it's going to be related to the Higgs vector. So we're going to define here the Higgs vector space, or sorry, the space of Higgs vectors, or the type of Higgs vectors, basically every element of which corresponds to a complex matrix, a complex vector of dimension 2. And on that, we are going to define an instance of a multiplicative action of the gauge group, which is here. That's to say that the gauge group, the global gauge group, I should say the gauge group here is the global gauge group, acts by a multiplicative action on Higgs vectors. And I want to write down and I want to prove this theorem here. This theorem states that this action is unitary or acts unitarily on these Higgs vectors with respect to the inner product on the Higgs vectors. And this is kind of the general form of a lemma in Lean. So you've got the statement here, and you've got some variables like input variables here. There, you could think of them as part of this if you wanted to. And kind of the aim of the game, or what we're trying to do, is we're trying to construct an element of this type. Or in other words, we're going to try and turn this thing here into being true. And we're going to do that using some tactics that Lean has that we can use to manipulate these equations. And this is where this thing on the right-hand side becomes important, because you'll see that if I put my cursor after this by thing, I get this here. And this is something called the tactic state. This tells me what I'm trying to prove, this thing here, and everything I have at my disposal, these things here. I can introduce new things if I wanted to. I can use lemmas that have already been defined above, and I can add them to my tactic state. But I can only do things that are mathematically well defined, and I can only do things that I can only use results that I proved before or that I'm assuming. In this specific case, the proof here follows using a tactic called calc, which is something like calculation. So we're going to do it by step-by-step calculation. And I won't go through the details, but basically the proof is says, okay, we're going to rewrite this as a dot product, which is this RW means rewrite. And if I put my cursor to the left of it, you'll see the thing we're trying to prove. And if I put my cursor to the right of it, you'll see there's no goals here, which is good. We'll then do some rearranging and so on and so forth. And basically, we're going to move the matrices to the left, and we're going to cancel them out by the fact that these are unitary matrices, and a matrix times the Hermitian conjugate of itself is equal to the identity. And this is kind of what these proofs look like. And it depends on these tactics like simp, which is, if you're familiar with Mathematica, is something like simp, simplify in Mathematica, so on and so forth. And this is kind of what Lean looks like. At the end of this file, there is the proof of the statement that if you have a unitary, an invariant potential of the Higgs vector field, and it has terms up to mass dimension n, then it can be written as the sum of norms of the Higgs vector to an even power. So in 500 lines, you can prove a result that's pretty relevant to physics. And this is just importing Mathlib. It's not importing anything else. So this hopefully shows you a bit about how Lean works. Hopefully shows you a bit about what you can do with it, and hopefully convinces you that you can actually do some real world physics in. Like I said, if you didn't understand that, I understand that these things are difficult to follow in real time. Don't worry. You don't need to know any of that for what I'm going to say in the next part of the talk. When I used to give a version of this talk 3 months ago, I used to show this slide. This is a benchmark for AI doing formalization. It's something called the Putnam bench. My pronunciation is probably incorrect here. I think the Putnam is more correct. So this is the Putnam bench. The Putnam competition is a competition in North America to solve certain problems in mathematics. And 3 months ago, I used to give this talk, and the best was this one down here. It was DeepSeek Prover, and it had solved 47 out of 672 problems. And I used to state, AI, people talk about AI and formalization. It's good, but it's not really useful, so on and so forth. That has dramatically changed in the last couple of months. In the last couple of months, the best is this one here. It's done all but four of those problems. It has solved using AI. And we saw previously that open problems in mathematics have been solved using this feedback loop between AI and Lean. I think more of a telltale sign that we are getting to the point where AI is useful in writing code like this. Let me go back a slide. Is that nowadays I actually use AI to write this code. Historically, I was kind of somebody that didn't use AI to write my Lean code, but nowadays there are places where it produces better code than I do. It produces better proofs than I do. And so we're getting to the point where you can throw Claude a theorem like this, where you haven't given it the proof, and it will produce a pretty good proof of that result without you having to do anything. That is known to be mathematically correct, and it's known to be mathematically consistent, so you don't have to check it yourself. Goes back to the scalability sort of thing. Awesome. So that's kind of the sales pitch of interactive theorem provers. Let me come out of this. I want to say some other things about them because I'm not in the interactive theorem proof. I didn't start using interactive theorem proofs because of AI, and I understand that there's a complete spectrum of people that might be listening to this talk, and people that might be don't like AI, people that might love AI. So I wanted to say, even beyond the trust arguments, beyond anything to do with artificial intelligence, you get a bunch of stuff from using an interactive theorem prover. The first is tactic automation. I showed you a kind of a bit of this when I was giving the live demonstration, but in Lean, you can define these things called tactics. These automate proof steps. So proof steps that might be really common in mathematics, like proving something in ring theory, has a tactic. You don't have to prove that by hand. There's a rule that proves that result. You can think of this as the sorts of commands that you have in Mathlib, sorry, in Mathematica. You have the same in Mathlib. And because Lean has a very expressive language, the sorts of tactics that you can define to automate proof steps is great. And so that's one of the things. The second thing is searchability. If you wanted to find every time the Schrodinger equation appears in a paper on the archive, you would struggle. You would struggle because everyone will have defined the Schrodinger equation in different ways. They will have used different variables. They may have called it a different name. They may be using a different symbol for their partial derivatives and so on and so forth. In Lean, everything is searchable based on the underlying mathematical context of a result because Lean knows that mathematical context. It's not like LaTeX or Microsoft Word where they don't know the underlying mathematics of the results. Lean does, and you can use that to search for results. And the search engines called Lugal and other ones that allow you to search for results based on the underlying mathematics, not on what somebody happened to call it. And that's very powerful. The third reason, or the third benefit beyond trust, is reusability. The reason I kind of led with Mathlib is that those 100,000 theorems and those 200,000 theorems and 100,000 definitions in Mathlib are completely reusable throughout physics, throughout mathematics. You can use them to prove your results. This is incredibly powerful because it means that you only need to prove things once. And once somebody has proved that, and as long as they've done a good job about the right statement and the right definitions, then you're in a very powerful position to kind of build up iteratively on what other people have done. And this is kind of bringing the open source community into mathematics. The fourth thing, which sometimes goes overlooked, is about executability. Maybe not so much of relevance to some mathematical physicists, but in physics in general, we like writing simulations. We like writing programs that simulate stuff. And in Lean, the definitions that you saw, that actually can be executed. Not all the time, but a lot of the time, they can be executed, computable definitions that you can put in simulations. This means that you can have theorems that connect very directly into programs. And this is another reason why Lean is becoming popular, is that programmers are interested in proving stuff about programs using these sorts of languages. Awesome. Okay. So that's the first part of the talk. Let me go into part two, Physlib. So, you know, Mathlib was kind of the bringing of the open source community and the bringing of like that sort of philosophy into mathematics. Physlib is an attempt to do that for physics. It is there to be a foundation to create a corpus, a library of results of use to physicists that can be used to prove other things, that can be used to prove research-related results. So that we have something that we can all work on and we can all build together. So we're not all replicating each other's results, so that we can come up on a consensus, a trusted base of results from physics. This is a GitHub repository, and that's kind of the core of it. So if I go over here, it is something that you can go on, you can download, you can interact with. If you install Lean, you can, play around with this repository. You can contribute to it, you can make pull requests and so on and so forth. So that's kind of the main content of it. Yeah, and kind of as I said, the aim is to replicate the success of Mathlib, but for physics. I wanna do kind of like a deep dive into kind of the structure of Physlib. And that's to kind of hopefully give you an understanding of some of the benefits that this philosophy gives you, some of the kind of the ways that this project works, and hopefully to you understand that if you wanted to contribute, if you wanted to come and have an opinion about something, you would know how to do that. You would know kind of the broad overview of the project. So I'm going to start with the organization of it. There are kind of three key points to the organization. The first, and by far the most important, is that it is community run. That means that if you're looking at this talk and you're thinking, this Physlib project looks great, but I wish they did that differently. I wish they had this approach to this, whatever, if you come and say that, we can talk about it. We can integrate it as a community. This library is meant to be something for the community, something that the community has a say in how it runs. And by the community here, I really mean the physics community, as well as parts of the formalization community. Second thing is it's an open repository. Everything is developed openly where possible. So you'll see if you look at the activity of the project. Let me go back to it. Oops. You'll see over the last day or so. I mean, we've had a number of pull requests from different people. Some of who, I've never met, some of who I've never spoke to, all contributing to the project, all trying to build it. It's pretty active. We get a lot of pull requests, a lot of contributions a day, 5, 10. That's probably better than the exaggeration. 2, 3, maybe. It's probably the average nowadays. So it's something that's definitely active and definitely growing. And there's a discussion forum where we talk about things, we do design decisions, we talk about random other side projects that we have that might integrate with it, and so on and so forth. It's had over 70 contributors so far, and it's got over 270 people on the Physlib channel for this project. So that's kind of the high level, the organization of the project. I now want to go slightly further kind of down the rabbit hole of the structure and talk about the large scale structure. And this is basically to mention something that we are currently trialing. Sorry. That is that we have introduced something called Physlib Alpha. This is still part of the same repository, but the idea here is that Physlib, or the directory Physlib within the repository, is kind of the core, the foundational file system where everything that goes into it is carefully reviewed, carefully checked that it's easily maintainable, efficient, looks good, something that we can trust for the future. Physlib Alpha is within the same repository, but the idea here is that the review process is more like the archive than a journal, so that you can formalize something quickly, you can put it in there, and we can grow this project, maybe with the help of artificial intelligence or maybe by humans, but just to have something that's more a rapid development place that then we can feed up and put into Physlib Alpha, move stuff from Physlib Alpha to Physlib. So that's the kind of the two-scale project. Physlib Alpha might not stay. Something we're trialing, see how it goes. If it doesn't work, we'll get rid of it. Um, going further down, if you go into the project itself, you'll see these files. And this kind of I'm showing you this because it illustrates one of the key concepts of this project, which is that we are trying to do this, we're trying to build this for physicists so that the organization of the project is organized by physics. So the key directories you're seeing here are directories of relevance to physics. If you look at Mathlib, you see directories of relevance to mathematics. So here we've got classical mechanics, we've got condensed matter physics, cosmology, electromagnetism, so on and so forth. If you go further in, you get more fine-grained areas of those subjects. If you know about knowledge graphs, you can think of this as a bit of a knowledge graph going down into different areas of the area. Okay, so let me go one step further in and tell you a bit about the content philosophy of the project. I'm not going to show you the content just now. I'm going to wait a bit until the next part of the talk to show you the actual what's in the project so far. But I want to talk to you a bit about the philosophy of the project. One of the questions I get is all the time is why do we need Physlib when we have Mathlib, right? Why do we need two separate projects? Couldn't you just put everything that's in Physlib in Mathlib? My answer to that question is no, and my reason for the answer is that in physics we care about this thing called physics context. In mathematics, they only care about the mathematical context or content of a result, the actual statement of that result as a theorem, and the actual proof of that theorem or the actual definition as a mathematical statement, as a mathematical object. In physics, we care about the physics context that is put onto that result. An example of this is the two-dimensional complex vector space, which we saw earlier. That can have two different physics contexts. It can have the fact that it's the Hilbert space of a qubit, or it can have the fact that it's the target space of or the fiber of the Higgs principal bundle. Two spaces, two vector spaces which are equivalent mathematically means something very different depending on what area of physics you have. So one of the key parts of Physlib is to put that physics context within the project. And we do that, first of all, by the organization of the project, which I showed you the previous slide. Secondly, by putting physics names of results. So we saw the Higgs vect, meaning the type of Higgs vector space or the type of Higgs vectors. We didn't call that Euclidean space 2 dimensions or something like that. We put the physics notion, we put the physics meaning there because that is what's most useful for the physicists. The third thing is we write physics documentation. Lots of parts of physics, if you look at a paper, they look more like Moby Dick than they do like a maths paper. They're written in prose, they're written in paragraphs. Maybe this is not so much true for the more mathematical of us, but large parts of physics, we write papers as people write books. We don't do definitions and theorems. There is a reason for that, and that reason is because lots of physicists care about this physics context. Lots of physicists care about this physics intuition that goes onto the project. So it's important, or into papers. So it's important that we include this within the project. The fourth thing is physics references to the physics literature. We can't include everything. So referencing results to the physics literature. And hopefully one day, we might get a situation where if there's a result in Physlib, somebody will be referencing that result from their paper to see, actually, yes, this is true. This has been verified to be correct. Cool. So, and then the fifth thing, which I won't say a lot on, is computable definitions. Aiming where possible to have definitions that you can actually use to write code if you wanted to do that. Not everyone does. It's not always possible, but where possible, we try and do that. So that's kind of the first part of the content philosophy that I want to talk about. The second part is probably more important. And this is kind of the approach to formalization. I'm just going to take some water a second. So one of the key things, one of the key confusions I get when I talk about Physlib and I talk about formalizing physics into Lean is that people automatically think that I'm talking about axiomizing physics. That means doing something like axiomatic QFT or, topological field theory or some sort of axiomatic version of quantum field theory. You can do that, but that's not what Physlib is about. That has a space within Physlib, but that's not exclusively all of the results that we have in Physlib. And the reason for this is that if you take that approach, you immediately limit yourself in the scope of what else you can do. Whereas if you take a different approach, which I'll explain in a second, you let yourself be much more flexible to do research level physics right now, rather than having to wait until we sorted out all of the foundations. So the approach to formalization that we have in Physlib is basically, I'll put them all on the slide. It's basically the same way that we write a paper. If we were to write a physics paper, we would pick a starting point for that paper. There'll be some implicit assumptions, some implicit stuff that, everyone in the field knows about that paper. And you take that starting point when you write a paper, and then you go from there, you define stuff, you make you write down your calculation, you write down your theorem, and you prove your theorem. When you're writing a physics paper, you don't go all the way back to axiomatic QFT or some other foundation. We follow the same approach in Physlib. You choose your starting point, you take that starting point, you derive results from that starting point, and then in the future, maybe we'll move that starting point further and further back until we all collect them in a theory of everything or something else. But that's not the point right now. Right now, we're saying you can write these, you can do these formalizations as if you were doing a paper. You don't have to, bring everything back to an axiomatic version of physics. And this is kind of just if you didn't follow this philosophy, you would immediately constrain the number of physicists that would be able to contribute to the project. And you'd immediately constrain the usefulness of it to those that are interested in a specific area. Cool. So I wanna swing back out a bit now and talk about some of the infrastructure, and this kind of sits on top of the project. I'm gonna mention them kind of quickly, but there's a bunch of infrastructure on top of the project that is kind of like adjacent to help one interact with it, to help one explore it. We've got search engines. Lean Explorer is an AI search engine. We've got Physlib Search, which is one made specifically for Physlib, which is an AI one as well. Actually, I think Lean Explorer is slightly more than AI. It also does it based on syntax. We don't have a version of Lugal, but Lugal is very useful for searching math results. We've got documentation. So it kind of gives a more friendly way to look at the project than looking at the code itself. We've got a to-do list. We've got things like informal results and lemmas and things like that. And kind of the to-do list is kind of the start, like one of the ways that people can get involved in the project, either by writing to-dos in an area of their expertise, or kind of trying to come and fill the project out. Okay, so the final part of the talk, I want to talk about, some of the content of the project. So far I've shown you one file and I've told you about the structure of the project, but I haven't proven to you that there's actually content in the project. So let me prove to you now that there is actually some stuff within the project. It's not just, nothing I'm talking about. I'm going to do this using this graph, and you will not be able to see this. This is blurry on my screen, so it's probably even blurrier on your screen. But hopefully you can see some of the regions. This is slightly old now. It's probably about 6 months old, but this is a plot of the content of Physlib. It's actually called Physlib back then, I think, but this is kind of shows you the areas where there's quite a lot of stuff, areas where there's less stuff, areas that we could have more stuff and things like this. So this big block on the right-hand side is quantum field theory. It's got things related to anomaly cancellation, specifically related to Diophantine equations. And the reason that's in there is it happens to be what I did my PhD on, and that was the first thing that was kind of in this project. So that's kind of just an accident that, that's where my expertise lied. It was kind of the starting point of the project, and that's kind of where it grew out. We've also got in that area Wick's theorem, a version of Wick's theorem. It's probably not the version that most people, it's probably not a version that's applicable to everything, so it probably needs to be generalized, but we have a version of Wick's theorem. We've got relativity here. This gives us index notation. as a physicist would do it. It gives us things like file fermions, left-handed, right-handed file fermions, the Lorentz group, um, things like that. Got some particle physics. The two Higgs doublet model, the Higgs potential, you know, more stuff about anomaly cancellation, the CKM matrix from the standard model, a general library of mathematics where we've got variational calculus, done in the way that the physicists would understand variational calculus to be done, not in the kind of the more mathematical way. Hopefully one day we'll link the two. We've got results from string theory, and this was kind of described in a paper with Sven Krippendorf. We've got some quantum mechanics. This area has grown a lot recently, as well as electromagnetism, which has already grown a lot. For electromagnetism, we have distributional electromagnetism, allowing you to do things like the Dirac delta function, infinite wires, where you're approximating things to be infinitely thin, as well as functional electromagnetism, and relating that to, field strengths, deriving everything from the electromagnetic potential. And so on and so forth. Some areas in classical mechanics, not that much stuff in condensed matter physics, not that much stuff in statistical mechanics, but some stuff. So to give you kind of like that's kind of like the overview to give you some specific results. We got the classical harmonic oscillator. Wouldn't really be a physics project if we didn't have the classical harmonic oscillator. But we've also got the quantum harmonic oscillator, and that's a quantum harmonic oscillator done completely rigorously. So that is like, where your Hilbert space is everywhere equivalence classes of almost everywhere equal square integral functions or something like that. You define the operators on that Hilbert space and so on and so forth. So we've done all of that. We've got the Hilbert space. We've got the quantum harmonic oscillator, the solutions to that. Schrödinger equation. We've got Maxwell's equations. I mentioned this before, derived basically from the Lagrangian of, the electromagnetic Lagrangian. We've got the Lorentz group. We've got the twin paradox. In special relativity. We've got the tight binding chain, which is something in condensed matter physics. We've got anomaly cancellation, which I've already mentioned. We've got the CKM matrix. We've got Wick's theorem. We've got string theory results. And we've got results from the 2x doublet model, so on and so forth. So if you want to look about what's in there in your favorite area of physics, there may not be that much, but you can have an explore. And if there's not that much, come and contribute, come and add to the project. Like I said, one of the key features of these things is that everything is reusable. So if you put stuff in the project, everyone can reuse that and build upon that to do their stuff. And if we haven't done something quite in the right way for what you want, tell us or talk with the community and we'll make the change. One of the features that made Mathlib so successful is that they weren't afraid to go, yes, we've done this incorrectly. It's going to take us a lot of work to fix it, but we are going to fix it. And we have the same philosophy in Physlib. If something is not done in the best way, we will fix it. Right? This is kind of the aim is to make a foundation, a trusted foundation that people can build, use AI on top of, formalize stuff that they want to on top of that we can trust and is as good as possible. And you can only do that if you iterate and you make mistakes and you change them as you go and as you learn new stuff. So this is kind of if you have access to the slides, they should be in the chat. This is kind of just a way that you can explore the structure of the project on the slides. But I wanted to say here, and this is kind of the reason I put this title, is that, we're not going after single results in this project. We're not going after the big headline results. We're not going after that thing that's going to, get us the next paper or all of that. What we're trying to do is we're trying to build foundations. We're trying to build a library that is reusable for everyone, is as good quality as possible. And that means, if you're doing electromagnetism, right? You don't just go for Maxwell's equations. You go, okay, let me take the electromagnetic potential. Let me write down everything anyone would possibly want to know about the electromagnetic potential. This is the same way that computer scientists build libraries. It's very different from how physicists write papers. Physicists write papers, they go after a single result. Computer scientists write a library, they say, I want to build something about lists. They write everything they possibly would ever need about lists. That approach, the computer science approach, works a lot better in this setting. So here we've got, random results. I think, we've got the definition of the electromagnetic potential, constructing that from the scalar potential, constructing that from the static scalar potential, constructing that from the vector potential, constructing that from the static vector potential, constructing that from a scalar potential and a static vector potential, so on and so forth, right? And for all of those, you've got lemmas, you've got other results that make it as easy as possible for somebody else to be able to use this. Um, so kind of my penultimate slide is, this is kind of meant to be a community effort. If you are interested in formalization, I urge you to please come and join this community. The more we work together on this, the better it becomes for everyone. There's no point, in my opinion, in having a fragmented ecosystem when everything is reusable and everyone can build on top of one another. So come join the community, come be part of the community. You can contribute on the Physlib. You can come to the GitHub. If you want to contribute straight to Physlib, do that. If you want to try this more relaxed Physlib Alpha thing, try that. But yeah, cool. So that's all I had to say. Happy to take questions. Yeah.
So thank you very much for this beautiful talk. Are there questions, comments? Please just unmute yourself and ask.
That's perhaps something. So you partially addressed this, but I was wondering if you could say a little more about how do you avoid um, excessive overlap with what's already in Mathlib? So for instance, I was looking around a little bit and I
Yep.
see, for instance, you have a definition of Hilbert space,
Yes.
which that exists in Mathlib. It's not called a Hilbert space because in Mathlib they don't use names, but
Yes,
it's
we had
there.
so yeah. I think our definition of a Hilbert space will be Hilbert. I'm not entirely sure where you're looking, but I'm assuming it's going to be the Hilbert. It's going to be a specific case of the Hilbert space corresponding to the Hilbert space of functions from space to so it'd be like the Hilbert space of square integrable functions from space to C. So that's a specific instance of the Hilbert space that's useful to physics. But to answer your question more directly, we will always be downstream of Mathlib. So if something goes into Mathlib, we will not replicate it. Right? We see Mathlib as kind of like the foundation. So if the general definition, if our exact definition of a Hilbert space was in Mathlib, we wouldn't redefine it. But if we want to take their definition of a Hilbert space and we want to go, actually, it is useful to define this specific instance of a Hilbert space, and define a bunch of properties related to that Hilbert space because that's of use to and of interest to the physicists, we will do that. Mathlib, they tend to have this policy where they focus on generality, so that they'll always do the most general thing. And in some cases in physics, you want to do specifics because it just makes your life easier. But in general, if something's in Mathlib, we won't reproduce it unless we're doing a specific form.
I mean, if I remember correctly, in Mathlib, there's a theorem that says that 3 is larger than 2 or something like that. So that they also do very specific theorems
I
that are
would
useful for proof.
Yeah, I don't know. In general, I mean, all I can say that it's a general philosophy is to do things more generally.
Mhm.
But like if they were like if Mathlib comes or people from Mathlib come and says actually yes we're happy to take that into Mathlib, that's fine. We're not trying to like if it goes into Mathlib we're dependent, we're downstream of Mathlib, so we'll just use the result as it is in Mathlib. It's not like we're trying to compete or anything. We're like the stuff can go up if it wants.
I have a question. Is this Physlib fully searchable? If I want to ask, for example, what is spin in six in the space-time of dimension six? What are the representation of spin in the dimension six? Can I find it by some searching? Or what is the procedure to
Well,
find
okay.
the appropriate
Yes.
group, for example?
Yeah, okay. So let me show you an example. So you wouldn't be able to find that result because it's not invisible, but I can give you an example. There are two kind of search engines for Lean. The first is kind of like a syntactical search engine. This we used to have a version of this for Physlib, but that cost money to run a server, and I kind of couldn't justify the cost. So this one is only for Mathlib, but you can search for like if I wanted. I don't know. Let's say I wanted a result related to modules and matrix determinant. I don't know if there will be any. Oop. So what this search engine has done is I've given it two concepts in mathematics. I've given it the concept of a module, a vector space, and given it the concept of a matrix determinant. I know how those things are defined. I know the nomenclature of Mathlib, so I know how to write those down. But that's a bit of a learning curve, knowing what to search for. But then I get here every result in Mathlib that depends on a module and the determinant of a matrix. So this is one way you can search for stuff, and I find this very powerful. Like if I want a result in Mathlib, I just think, okay, what is that result gonna depend on? And if I end up getting like 2,000 of these, I'll add more stuff to be more specific. Um, but in a lot of cases, there's only a small number. So that's one type of search engine. The other type of search engine is one which is driven by AI. This doesn't have this is kind of using the structure of the library, but it's not using the underlying lean language to find results. But for example, if in this one I could write something like Higgs boson potential, and I would get results with a summary related to the Higgs boson potential. And I think I should be able to click through to the definition to the documentation, which is here. I should say I did not make this search engine. Somebody else made this. But yeah, this is, and there are other ones as well. But this is the other way that people search lean. And I think this search engine should hopefully be useful to you even if you don't know lean, right? Like it is getting the kind of the knowledge, the source of truth from the project. But you don't need lean to read. You don't need to know lean to read that. Maybe you do a bit to understand what that means. But ideally, these search engines should be. You should be able to search for results without knowing lean, and that is something that kind of could be beneficial to the community. So yeah.
Okay, thanks.
So, any other questions?
Yes. So I'm sure this is a frequently asked naive question, but why is lean reliable? Why can we believe that lean is correct?
Yeah, okay. Yeah, this I probably did a bad job of explaining this. I
Mm,
my live.lean thing is I used to do the natural numbers in this example. But then I realized that actually maybe doing something related to physics would be better. Okay, so the way that lean works is that it knows the type of everything. So it knows what, the set that everything belongs to.
mm,
And in lean, a type is a type, so every type is also an element of the type. And all that lean is doing is that it's going, I've got a space. I know what type
mhm,
should go in that space. The user has given me something. I'm just going to check that the thing that they have given me
mm,
is it matches the type that I'm expecting. And that's basically all it's doing. So you can the underlying principle of how these
mm,
things work is really simple. So you
okay.
can
Mm,
and the implementation of that type checker is really small and easy to check. Not only that, other people have independent type checkers that you can put onto Lean and check it on your own terms, on your own type checkers.
Mm-hmm.
You can introduce axioms. You can introduce axioms like false. And if you introduce an axiom false, you can prove anything. But there are ways to check for those. So if I take this lemma here, I'm going to have to refresh. If I take a proof, let me take this one. I can print the axioms that formed that proof, and you will see that it depends on these three things here. And those are the kind of the three standard axioms of Lean. So I know that I haven't done anything naughty. There are more sophisticated checks that you can do, but you know the kind of the foundation has been tested and proved, and the underlying mathematics is really simple. All it's doing is just type checking. So like even in the proofs, all of these tactics, all they're doing is they're just producing a massive term, like something like this. And at each point in this term, you know, it knows what everything is. And it's just checking, is that the type that I was expecting at that point? The
So,
beauty,
but can you also treat something like abstract inductive proof by using only this kind of type matching?
like induction, proof by
Yes.
induction. Yeah, so
Yes.
Lean is based on an inductive type theory, which means you can do proof by induction.
Okay.
In fact, it's probably the easiest type of proof to do in Lean is proof by induction. I don't know the status of co-induction. I think that I'm not sure. Yeah, there's been talk about that in Lean, but that's more tricky. But proof by induction is easy and trivial.
Yes. So anyway, you can rely on this. Good.
Yeah. And out of the 100,000 or 200,000 theorems in Mathlib, I don't think anyone's been surprised by the truth. Like no one's been able to prove something that, you know, we know to be not true or something like that. You know, not only are the foundations simple enough that they're really easy to check, you know, they've been proved by massive amounts of example.
So maybe following up on this question, what I always hear from leaners is that it is much harder to write correct definitions in Lean than in traditional mathematics, because you have to exclude by hand many cases which we exclude somehow implicitly by common sense in traditional mathematics. So somehow you did not emphasize this problem. Do you think there is such a problem, or it's maybe exaggerated worries?
No, okay. I think I wouldn't call it a problem. I would call it a challenge. And that's just rephrasing that stuff in a more positive
That's
light.
wording.
But yeah. Okay, it's definitely hard to write good definitions in Lean. There is no doubt about that. Like it is hard to write a good definition that matches, I mean, in physics especially, that matches the underlying physics, that is easy to use, and you know does everything you want it to do. That is a generally hard problem, and this people are saying that you know there have been endless discussions about this, about AIs can obviously prove theorems, but can they write good definitions in Lean?
Yes.
You know, people would debate whether we're there now or not. But it's certainly the case that the definitions need to be checked. You need to understand what goes into the definitions. The sort of the edge cases that you were discussing, I would say that doesn't come up so much in physics. That more comes up in the case where you know you want the natural numbers. In Lean, the natural numbers include zero, but actually you don't want them to include zero, but you're a bit careless with the definition, and then you include zero. There's been cases of this, and then you can prove this open conjecture because the conjecture assumed zero wasn't included, but you've included zero. So there's cases like this. But that's one of the things that I like to say is that Lean does not stop you being stupid. It just stops you being incorrectly stupid. Or it just stops you being incorrect. So you can put rubbish definitions in. You can prove rubbish theorems about those rubbish definitions. It doesn't stop you doing any of that. It will just make sure you're mathematically consistent, right? And you know, I have had people email me dubious physical theories that are mathematically correct, and they're formalized in Lean. Lean doesn't say anything, and this is part of why this trust diagram I put doesn't go all the way to the top. Lean doesn't check whether the definition that you wrote down corresponds to the definition that you wanted to write down. If that makes sense. Like
Yeah,
the
okay, but now from a practical point of view, when people or physicists put on the archive some mathematical result obtained
yeah,
by auto-formalization, there is some code produced by the AI, which is
yeah,
not accepted to Mathlib library and
yeah,
contains some definitions inside,
yeah,
also produced by the
yeah,
AI from fields of mathematics,
yeah,
which the physicists probably never learned. Should I
yeah.
trust this or not?
I would probably say no.
Okay.
And this is why you need these trusted libraries. This is why you need Mathlib. This is why you need
Okay.
Physlib. This is why you need these libraries that have been looked at and looked at and looked at. So you've got these trusted definitions so that other people can use them. Whenever you see lean code, you should check the definitions.
Mhm.
Like don't the definitions and kind of the assumptions that go into that are the key, and you can fake them, and somebody might have put something that they think is correct but it's not, right? There is content in the definitions that needs to be checked. So in my opinion, and this is opinion, if you just take a physics paper, and you go, let me auto formalize this, you don't look
Mhm.
at the lean code and you go, yeah, the lean code compiles.
Yeah.
That doesn't tell you much. Because
Right.
you don't need you need to look at the definitions. You need to and the theorem statements and all of that to check that it's actually done the right thing. Um,
Mhm. Okay.
You mean you human, we have to check by ourselves.
I mean, I would say yes. I mean, you get people
Mm.
that say you can get an AI, like you do this AI review type thing.
Mm.
I mean, it depends where your level of trust comes in. I mean, my personally, I would want trust by humans, but I understand that other people, an AI review, it's good enough.
Mm.
Um, that's like a personal choice. Um,
Mm. Mm.
but this
But
is why I kind of like if we have a foundation of definitions we can trust, and we can make sure that these auto-formalized results just
mm.
depend on the definitions in the trusted library,
Mhm.
then you don't need to check them. Because as long as you've got the trust a library which is trusted by the community,
Mm.
then and you've done an easy check that the auto-formalization is the um just uses those definitions, then you're pretty good. You have to check that the theorem statements are correct. But
But in your
Okay.
case, you have many things in Physlib alpha, and
yeah.
then if you trust, you move it to Physlib.
So
But
Physlib Alpha is very new,
uh-huh.
like a week old, let's say. So
Hmm.
there's not so massive. Most of the stuff is in Physlib right now. But yeah, ideally stuff that goes into Physlib Alpha, when we trust it, when it's like good enough quality, we'll move it over to Physlib.
Yeah, yeah. But that's judgment is done by who? Your
So
community? Yeah.
the project
Mm.
the project has a review system.
Hmm.
So every pull request has to be, we've got 7 maintainers of the project. Everything that goes into the project has to be checked by one of those.
Hmm.
Anyone can review it, but it has to be approved by one of the 7 maintainers. And like I can't approve, like I'm a maintainer of the project, I can't approve my own PRs, my own pull requests. Sorry. I can't approve my own contribution. They have to be reviewed by somebody else. So everything, except in the early days where this wasn't the case, but nowadays, like everything that goes into Physlib, the main part is reviewed and
Hmm.
checked and all of that. Things that go into Physlib Alpha, we do what's called a one look review. This is stealing a term from the archive. That is to go, is this mainstream physics? Because otherwise you're just going to get junk, basically. Um,
Hmm.
and then it goes into Physlib alpha. So don't trust, you shouldn't trust Physlib alpha as much as you trust Physlib. They're in the same repo. They're just distinct file systems.
Mhm.
Okay, any other questions?
Yeah, maybe I have a question in a slightly different direction. How do you handle author credits? I mean, it's a lot of work to do this, and if what you imagine comes true, then I mean, many people will contribute to and formalize parts of physics. So do you keep track of authors, or do they get
Very
credits,
good,
or
yeah. Very good question. So, okay, the first thing to state is anything that goes into Physlib, we have no claim over the authorship. So if you want to formalize something, that's your formalization. There's no one from the Physlib community is going to be like, I want to be on that paper because you formalized it, right? So what you formalized, and this is kind of taken from Mathlib. If you formalized X, that's yours, right? You write a paper on that. You don't need to put anyone from Physlib on it or anything like that. There is a lot of surface work that goes into Physlib, kind of like the more foundations. Like today, I spent 7 hours trying to move it to the next version of Lean. That sort of stuff. We're thinking about how to give people credit for that sort of stuff. And one of the ideas, which isn't mine, is to but I think it's a good idea, is to every now and then write a summary paper where we go, this is what's happened on Physlib for the last year or so. These are the people that have contributed. They're all authors on the paper. This is the work that they've done. So it's kind of adjacent to the actual paper set you might write about specific stuff. That's more of the like to credit the people that are doing the surface work type of thing. So that's the scope. But if you put stuff into Physlib, don't like we're not going to claim, we're not going to be running after people about authors or anything like that. It stays them, they can write the paper. It's all of that. Like it's kind of just general academic epithet, I guess.
Okay, any other questions? Okay, then maybe following up on the last question. Okay, suppose I wanted to switch from mathematical physics to formalization and now work full-time on formalization. Where do you publish the summaries? There are some special journals for formalization, or?
So yeah, this is a good question, and this is a hard question. So I have tried to put these sorts of papers in, so not the summaries, but even just like I formalized this for SALT
Yes, yes.
into physics type papers. I tried to put them into the more traditional high energy physics journals like JHEP and stuff like that. They don't accept it. That's their policy. And it's because they want new physics, and
Uh-huh.
these things don't contain new physics in their sense. I would argue that they do. So the places that I found are more of the like computation, like I've forgotten the names of them. Is the thing. So computer programs in physics. There is a formalization specific one that I've spoken to the editors before, and they said they're willing to accept physics papers. There's a bunch of um, mathematics and computer science journals that take this sort of
Uh-huh.
stuff. So there are journals, and like I've spoken to the editors of a bunch of these who have all said to me that they are willing to accept these sorts of stuff.
Uh-huh.
So there are outlets that maybe just not the traditional ones.
Uh-huh. Okay, I see, but still it's sort of a problem because it means effectively disappearing from your previous community, which would be, in my case, mathematical physics, and trying to attach to some other community which seems a bit scattered. I mean, some
Yeah,
journals
I mean,
accept, other don't.
I know, yeah. I mean, this is the question I mean, I would love it if these journals would accept these sorts of
Uh-huh.
stuff.
But isn't
I
there some middle way, like doing new physics and in the same time
Sure, yeah.
developing?
Oh, yeah, yeah, yeah. Yeah, so I mean, let me um so this paper this paper was basically this, right? We
Uh-huh.
formalized stuff, but we also did new physics. Um
Okay.
so yeah, you can do both at the same time.
Okay.
Um
And then journals like JHAP may potentially take it, or it's also not so sure.
Undetermined.
Undetermined.
We're
Okay.
yet to submit this one. Our plan is to submit this one to JHAP.
Okay.
Undetermined.
So
Um,
it's experimental. Okay, but
I
in
think
general,
I think that from what I've heard from the people that work on machine learning and physics, they've also had this sort of struggle where the more traditional physics journals don't
uh-huh,
take these sorts of works. Um, yeah.
uh-huh, uh-huh.
So
Um,
it's a common thing.
Okay, okay, I see. I'm basically wondering more from the side of mathematics. I have no hands-on experience so far, but I'm wondering if it's possible to have like to use these tools so that I
Mhm.
am effectively doing what I have been doing so far. So
Yeah,
imagine I want to,
yeah,
solve some particular equations or prove
yeah,
existence of
yeah,
solutions to some equations, for example. So I want to continue doing this,
yeah,
but using these tools, I want to be both more rigorous and
yeah,
faster. So my
yeah,
impression when I look at all this is that it will slow me down to zero if I even try to learn it. Uh, Especially, the traditional lean without AI was like, I don't know, 10
I think
times
that that's
slower
true.
than
Yeah, I think this is
now.
true. I think with AI, I think with AI that calculation has dramatically changed. I think
Okay.
with AI, it's going to be slower because you're producing something which is more verified.
Uh-huh.
But I think it was a factor of five in the past. Maybe it's a factor of one and a half now.
Okay.
AI and sometimes like these AIs like generally do help you prove stuff. Like if I was to prove something from physics, I would use Lee. Like even if I was doing normal physics. But I think your use case where you're saying you've got a calculation or you've got a derivation, you've got a proof that you were going to do anyway,
Uh-huh.
and you were going to write a paper on it anyway. I think that's the perfect use case for this. And like
Uh-huh.
that sort of stuff is more than welcome in Physlib, kind of because of this formalization philosophy. And so then
Uh-huh.
somebody could build on it and take it on, or you could build on it and take it on in the future. And like depending on what the area of mathematics is, that might be
Uh-huh.
very easy. It might be very easy to down these equations, write down these calculations, write down these derivations, and it might be very easy to get the AI to do it. On the other hand, it might not be. Like it's quite variable.
Okay, yeah, but yeah, as I said with AI, my worry is that that I will miss something in a definition, but it will fool me in a sense. That if I rely too much on AI, that
Yeah. So one way to get around this is to so I'm a category theorist like when I used to do physics, and it's a bit weird, but I used to do category theory in physics. And one of the things there is this thing called the dilemma, and that basically says that a definition is defined by its properties, not by the actual definition itself. So if you're worried about being fooled or anything, just make sure you've proven enough things about your definition that
no.
only the correct definition would have been able to
Uh,
satisfy those lemmas. That gives you a very good like litmus test about what
Yeah,
you
yeah.
think.
So I saw this attitude in these physics papers, which I mentioned. It's very much how physicists think about numerics. If I check it in five
Yeah,
exactly solvable models,
yeah,
then it
yeah.
is okay. But this is not how we think in mathematics.
No,
Although
no.
in reality, our brains are finite, so we can also test our definitions only in a finite number of cases.
Yeah.
But we believe that we do better than that.
Yeah, I mean, okay. The other way is then, take your definition. Don't define massive definitions. Define really small definitions where you can, or ask the AI to define really small definitions. And this is kind of what like Lean does. I mean, this is kind of the whole library philosophy. Is you don't go for the end result. You kind of build things up in a reliable way, and as long as you can kind of like check each of the definitions. I would also say like it's not that hard to get the right definition. I mean,
Okay.
there's a lot of like it's you will like yeah, it's not like it's impossible to get the right definition. It's easy to get the right definition. You just have to be a bit careful. It's not
Okay.
like yeah, it's not
Maybe
something to be overly worried about, I would say.
I see. But maybe other people have some questions still or remarks? Okay, if it's not the case, then maybe we thank Joseph again. Thanks a lot, really very interesting talk. Then we can switch off the recording and maybe in an informal discussion, people will be less worried to ask questions.